Okay, Assalamualaikum and good morning. So today we'll continue with our lecture on special relativity. So let me just share the screen first. Okay, let me open the notes. So can you see the notes?
Yeah.
Okay, so we have gone past, so this is Galilean relativity. We have gone past defining inertial frame in classical mechanics and also the transformations that sort of keep your Newton's equation Newton's equation and second law to be invariant, and there are already mentioned about the four different transformations that allow that Newton's equation to be invariant. Okay, so we'll continue with this, and what we're going to do is probably, I think we have gone through rotation group. Okay, so rotation is one of Galilean transformation. And it obeys what we call the group law, okay, which is given by this called properties, okay, closure, associativity, identity, and inverse. And we have shown that in the case of rotation group, we call it as a special orthogonal group. And if you include reflection, it's simply called orthogonal. Okay, so we have seen that in the past lecture. So today we are going to look at the case of the Galilean transformation. So remember the four different transformations that we had was space translation, time translation, and then the other one is uniform motion, and finally is the rotation. Okay, so now if one were just to use the coordinates of position, then we'll find that one of the things that will be left out is essentially your time translation. Okay, and also without time coordinate inside your uh, parametrizing your event, okay, then you won't be able to actually see the Galilean transformation under uniform motion. Okay, so we need to time, but also what we're going to do is so we have position here, okay, given by Ri, where I equals to 1, 2, 3, okay, and then you have your time, but we also include the 1 here in order for us to actually allow what we call the Galilean transformation of constant space translation by a constant and time translation by a constant. So we have to actually use the idea of a constant is related to this particular one over here. Okay, so we're going to parameterize our coordinates in such a way. Okay, so time is now included, despite that time generally thought in classical mechanics as just simply a parameter rather than a variable. Okay, so now we include time and also that particular. So this is for time that will come into your time translation as well as uniform motion. Okay, and in order for us to have this constant time translation as well as constant space translation, then we also add this one to allow constants. Okay. So otherwise, if we just simply use your Ri, then we are only limited to the rotations. Because you think of a 3 by 3 matrix multiplied by a 3 by 1 matrix, just your Ri, then you get a 3 by 1 matrix, and that is not enough for the Galilean transformation. So the Galilean transformation will have this 4 parameters, including this one will be 5. Okay, so the matrix that multiply this 5, so this is actually a 5 by 1 matrix. Okay, 3 here, 1 here, and another 1 here. Okay, so in order for us to have the Galilean transformation written as a matrix, we need a 5 by 5 matrix. So this is 5 by 5 matrix, this is 5 by 1 matrix, and then it ends up with a 5 by 1 matrix. Okay, so over here you can actually see what's happening here is this part is actually a 3 by 3 block. This will be a 3 by 1 block. Is it? Yeah, I think it's 3 by 1 block. And the rest are 1 by 1. Okay, so this is just a 1 by 1 matrix here, 1 by 1 matrix here, and so on for the rest. Okay, so when it multiplies this 5 by 1 matrix, this will multiply Rj, for example, to give you that part. Vi will multiply by T, and then R naught I will multiply the 1 to give this that thing. So this will correspond to your space translation. See how it acts on the 1. Okay. And then the T will multiply the velocity here. So this is your uniform motion. And then this one, essentially just your rotation. Okay. And finally, we also have this one. So this is actually, this one is actually a 3 by 1. Okay. And then we have this. So this is 1 by 1, 1 by 1. Sorry, this is let me think carefully. It's going to be one by 3. Okay, so 1 by 3, and then this is 3 by 1. Okay, so this 1 by 3 act on this 3 by 1 will give you 1 by 1, but it's 0. Okay, and then this 1 will act on this T to give you T, then this T naught acts on this 1 to give T naught over here. And so in other words, we also have the time translation. So remember, we had 4 different transformation for Galilean transformation. So we have already all the four: rotation, uniform motion, space translation, and time translation. Okay. So this is just a convenient way of writing down the Galilean transformation. If one had only uh, R and T, then we cannot get all these terms here. So that's why we have that one to allow you to have this addition of your constants at the spatial part and also the time part. Okay. Later on, probably I'll give you an exercise to do the same for special relativity. Okay. So, right. So, this matrix is now a matrix that represents a Galilean transformation. Just like rotation matrix represents your rotations. Okay. And we claim that this Galilean transformation forms a group. So one of the things that we need to check from the idea of a group has to be closure. Okay. So we need to do that first, so that all your transformation will just be contained in itself. So here's a 5 by 1 matrix, so it's 5 by 5 matrix, another 5 by 5 matrix. Okay, multiply them together and then you get a 5 by 5 matrix. And essentially you can see what's happening here. Remember that this part, this is a 3 by 3 block, this is a 3 by 3 block. You multiply each other, that just gives you another 3 by 3 block, which represents your rotation. Okay, but you'll see something non-trivial happening here. Here you find that, okay, my 3 by 3 block also multiplies the 3 by 1 block, okay, of the velocity coming from this velocity. Okay, and then it adds up this velocity. For the rest, you see again, this is a 3 by 1. So this is 3 by 3, 3 by 1. And then this is 3 by 1. And then this is 3 by 1. Okay. So again here you can see the uniform motion coming here. In other words, there is already the pattern of the Galilean transformation, even with the composite what you call matrices that defines the Galilean transformation. Okay, and then the other thing that we need to check, it is time translation part. So this is going to be multiplying that, for example. Okay, and then you find that, okay, this gives you T1 plus T0, which is the thing that you need for time, composition of time translation. And finally you just get your 0, 0, 1. Oops, this is 1, sorry. Okay, so again you can see that it has the same form. Okay, but you have some kind of non-trivial composition on the elements. Okay, so please change this what you call this element to be equals to 1. So that's my mistake. And what about the identity? So that's another element that we need to have. Well, it's just a identity matrix for replacing your rotation matrix. Okay, and then there is no uniform motion. Okay, and then there's no this part will be your space translation part. Okay, and then your time translation part here. So it just multiplies identity for each, okay, and the uniform motion, there's none there. So in other words, it doesn't do anything, okay. And for the inverse, this needs a little bit of algebra, but essentially what you need is to make sure that this is a Galilean transformation that we had earlier, okay. So we need one matrix that multiplies it to get this identity, and you can find out that this is the right inverse for, let's call this M, then this will be M inverse, okay. So in other words, all your Galilean transformation now are just matrices, and matrices is already associative, so you get rid another, well, I mean, you not get rid, you also satisfy the other what you call group properties, okay. So in other words, you have what we call the group of Galilean transformations. I'm not sure whether they have any name for it. Let me just search, see if there's any symbol for it. Yeah. Transformation. See, usually Wikipedia should have it. I'm just trying to find a notation for it, whether they have a notation for it. No specific notation. So it's just given as this symbol. Okay, never mind. So one with this Galilean group, or Galilean group, call it. This is sometimes called Galilean group. I think I had it somewhere. We can implement what we call Galilean relativity. Okay, so let's look at what are these implications of Galilean relativity. So here's one. Now suppose you have a body moving frame O dash. Suppose you have a body, so let's draw something here. So you have a body, so moving with velocity u in some frame O dash. So this is O dash, but the frame O dash is actually moving with uniform motion with respect to another frame. So I have another frame O here, and observer in this O frame will see this frame to be moving, okay, with velocity v here, okay. So then we allow it to coincide at t equals 0. So this is a wrong picture then. Let me, okay. The picture should be this kind of thing, okay. So this axis coincide. Well, I should have defined what this axis is supposed to be. This will be the axis of time here, okay. Is that right? Yeah. So this is going to be t dash. So this is going to be t. I'm coming from here, okay. And then the position, when I condense the position to a single dimension over here, okay. So what happens over here, then you'll see that, okay, we should be able to find out how do you see this object that's is already moving inside this moving frame, what would be the velocity? Okay. First, what we need to do is to coordinatize this body inside this O dash frame. So this body inside this O dash frame will have velocity here. So this is the velocity, and then it will multiply by time to give the coordinates in space, and then there will be a time within the O dash frame itself. Okay. And time in the O dash frame equals with the time in the O frame, because we say that these frames coincide at time t equals 0. So in other words, t dash, if I want to be particular, I should have written this as t dash, but t dash equals to t. Okay. So in this particular case, okay, this is a event coordinates of the body in O dash. So if I want to find the event coordinates of the body in O, what do I need to do is essentially to apply a Galilean transformation to this set of coordinates. Okay, so that this set coordinates are seen to be moving with respect to O. Okay, so the transformation that we need is essentially the transformation of a uniform motion. Okay, so we apply this transformation of uniform motion so that O will see O dash to be moving with respect to the frame O. Frame O dash is moving with respect to frame O. Okay, so that's what I wanted to say. So I applied that to these coordinates, then I should be able to get the event coordinates of the body with respect to O, and then you multiply this, then you'll find that, okay, the spatial coordinates will be given by ut plus vt. The time coordinates are just the same, okay, because they coincide at time t equals 0, and then this is just 1, which doesn't do anything there. Okay, so we might say, so what, right? Well, remember that this is supposed to be the spatial coordinates of the body in O frame. So if I take this spatial coordinates, take the time derivative of the spatial coordinates, then I should be able to get the velocity of the body in the O frame. And the velocity is simply u plus v, and this is logical because you had u already moving inside O dash and O dash moving with respect to O with velocity v. Then essentially you have what we call Galilean addition, well, it's over here, Galilean addition of velocities. Okay, so that tells us about the addition of velocity for a body moving inside a moving frame. Okay, now we have to see one other thing so that we can contrast this with what's happening in special relativity. You can actually see that, okay, in the context of this Galilean relativity for classical mechanics, one could actually, in fact, take an infinite velocity. Okay, you see that this is possible in classical mechanics. Okay, so in other words, if you find an infinite velocity body, means, I mean, it's difficult to think about it, but no, if you have this to be infinite velocity, then you also have this infinite velocity. Okay, that is how should I say, that is indicative of something. Well, I mean, in a sense, this is consistent with the fact that this is actually going to go to infinity, then you should have that go to infinity. Okay. But what is problematic over here is the fact that one could start thinking of frames moving at how should I say it? You can add velocities more and more, okay, by just thinking of a successive moving frames in such a way that these velocities will add up to infinity without your, well, I mean, how should I say? What I want to say is something happens with respect to this Galilean addition of velocities, so that you'll find that that your whatever this u plus velocities, okay, can exceed the velocity of light. This is allowed, okay, even though this u is actually less than velocity of light, but because of the addition of the velocities of the frame, so you can think of a consecutive moving frames. So one frame is moving with respect to another, and then that frame is also moving with respect to the other. So you add all these velocities, and then you be able to get a body that actually goes beyond the velocity of light. Okay, so that's the thing I wanted to say. Okay, so that's one implication. The next is the following thing. Suppose that you have frames O and O dash with a time difference. Okay, so in other words, O will have coordinate t. Okay, then O dash can have coordinate t dash, where t dash is not equals to t. Okay, so what can be done in this particular case? Well, one can perform what we call an inverse times translation transformation, which is a Galilean transformation. So what is an inverse time translation? It's just multiplying with this matrix to the matrix that coordinatize the event in the O dash frame, for example. Okay. So what's going to happen is that, okay, I can multiply this thing, and then I'll find that, okay, I'll be able to get the time coordinate, which is in the O frame. Remember that this is O dash frame, and then it is O frame. So I can always make correction if I know that, okay, that some other frames are actually having a different time coordinate. I can always make corrections in such a way that I can always synchronize the time for each frame. Okay, so in other words, in Galilean relativity, time synchronization is always possible due to this transformation. Okay. The next thing that we want to say is perhaps more of a labeling. Okay. Suppose we have two events. So one is with space coordinates r1, then time coordinate t1, and then the other event will be r2 and time coordinate t2. We can say that the two events are simultaneous. So this is just a label. What does it mean by a simultaneous event? Is the fact that that this T1 and T2 has to be identical. Okay, or in other words, delta T, which is the difference between T1 and T2, has to be equal to 0. Then we say that those events are essentially simultaneous. And then with respect to the spatial coordinates itself, we can say that two events coincide in space if the difference between the spatial coordinates here is going to be the zero vector. Okay, so these are just label. Why we are doing this label is the fact that later on this will change when you do special relativity. Okay. Okay. Excuse me. What else? Okay. The other thing is the fact that there's this concept of equivalence of initial frames from the Galilean transformation. Okay. And they signify something else. Okay. How should I say this? I think I should have done the other one. But never mind. Okay. They are actually signifying that the nature of space and time inside Newtonian mechanics are homogeneous. Okay. So what does it mean by homogeneous? Is the fact that any two coordinates of the events are how should I say, equivalent in some frame. Okay, it's a bit difficult for me to. So there is no special points inside the space and time in Newtonian mechanics. That's essentially what's trying to say. Okay. You can translate time, you can translate space, so there's no special origin, for example, for space or time coordinates. You can always do translation of both spatial coordinates and time coordinates. And the fact that the two is also another thing, the two is actually independent of each other. Your spatial translation is independent of your time translation. Okay, so that makes it a bit more freedom between the two variables. Okay, and in some picture, if you understand a slightly more mathematical viewpoint of space and time, you can think of your absolute space over here given by R3, okay, and then you have a time underneath that flows throughout this R3, giving you the time coordinate. So any event can be made to coincide at a particular t naught by just using time translation. Okay, if you want to. Okay, but that how should I say? I should be careful what I'm saying. So we can actually do a clock synchronization. Okay, so that is with respect to the idea of homogeneity of space and time, because no special points in some sense. And then the other thing is we start to think about length. Okay, so consider a length of a vector here. For example, you have two events, okay, in space and time. So this is R1, this is R2, and then I can do something like this as well. This is time coordinate, so this is T1, and this is T2. Okay, but our interest is in this vector here. Okay, that vector if you see, you will have certain length given by this s squared. So this is length squared really. So what you do is you take the difference R2 and R1 dot product itself, and you can write in this particular way given your x and y z coordinate this way. So I'm here again, perhaps if you remember the idea of contravariant vector, so this should be a contravariant vector, this should be a contravariant vector, but what I'm going to do, I'm going to turn one of them into a covariant vector so that this becomes a row matrix and this becomes a column matrix. So I get this form here and this form here, and then you get essentially the difference of your coordinates square sum together, and this is precisely your Euclidean geometry. Okay. That means your Pythagoras theorem works. Okay. So if you try to make any changes with respect to this spatial coordinates, say going to the reference frame O dash, then it will the thing that actually allow to be done for the spatial coordinates are rotations in this case, and then you find that okay, your length squared in this particular case will be preserved because your rotations over here will be an orthogonal matrix, and then you find that this A transpose coming from this part and this A is coming from that part, so it multiplies together and gives you identity. So it gives you identity, then you be able to get the original difference of the spatial coordinate time multiplied together, and that is actually delta s squared. So in other words, if I call this delta s dash squared, then I would have this preservation of the delta s. Okay, and the fact that you can actually rotate inertial frames, okay, is related to the idea of the nature of space being isotropic. What does it mean? It means you see space in all directions to be the same. Okay, previously all points are equivalent in a sense because there's no special points, and that's homogeneity. And for this particular case, no matter how you rotate it, everything looks the same. Okay, the space just looks the same. Then we call it as an isotropic space. Okay. Finally, let's consider the case where you have a reference frame O dash moving not in uniform motion but with some acceleration. So in other words, dv dt over here, dv dt over here is not equal to 0. So this is not uniform motion. So what actually happens in this particular case? So that means the frame is actually accelerating, and because the frame is accelerating, when you take the time derivative for h, so this is in the O dash frame, okay, the spatial coordinates in the O dash frame, you take the time derivative, then you find that your velocities add, which is your Galilean additional of velocities really, and then but when you do another time derivative, you should get your acceleration. Okay, so over here you have your acceleration coming from the coordinates, okay, but you also have the acceleration coming from the frame. So what actually happens over here, our expectation really is that I'm supposed to have the force just given by mass times acceleration, but actually you have force, okay, if you multiply m through r, so I get force equals mr double dash mr double dot me. Okay, so there's a hidden force coming from this acceleration of the frame. Somebody is coming in. And the force F minus this MA is called an initial force, and F minus MA is called an effective force. And the effective force essentially tells us how much it deviates from the Newton's second law. Okay? So in other words, what you have is not really an inertial frame. The accelerating frame is on an inertial frame, and they are called non-inertial frames. Okay? So non-inertial frames are not equivalent to an inertial frame. Okay? And finally, this is where one starts to think about something slightly beyond mechanics. You talk about propagation of light. So consider the case of a point source of light. So let me draw the three-dimensional first. So this is x, y, z, just to tell you what happens. Okay, initially I have a source of light over here, and then this is at time t equals 0, so the light source emits uniformly in all three dimensions. So what you have, if the light will propagate like a sphere kind of thing. Okay. So this would be your spherical waves. And the spherical waves are moving in all directions with the same velocity. Okay. So in other words, what we have is essentially, if you consider where the point on the sphere is supposed to be, okay, then you'll find that it should obey this particular equation. Okay, so in fact this is an equation of a sphere. Okay, the only difference in the usual equation of a sphere, this is supposed to be constant, but now this depends on time, because you find that your sphere is actually propagating in all directions. Okay, so what's going to happen in this particular case when you start considering moving frames, for example? Well, let's do this particular simplification first. First, what we're going to do, because we want to include the time axis, okay, so I'm going to take my time axis to be this vertical line. So I have to condense the three-dimensional axis that you find originally into a two-dimensional case. Okay, so in other words, I can say overlap my y and z as an example, then I can include your time axis. Okay, so in this when you have this time axis in this way, then this propagation, so remember that this is supposed to be the thing is going to propagate in a bigger and bigger sphere. So really what one has, your sphere in this particular case are your circles here. Okay, because I condense this two-dimensional into one-dimensional, so I get this circles representing these spheres, these enlarging spheres over time. Okay, and these spheres, okay, which is condensed from the three-dimensional case, these spheres forms what we call a light cone. Okay, and this idea of a light cone is very important in special relativity. Okay, so now let's apply a uniform motion to this particular propagation of light. Okay, so what's going to happen is that, okay, suppose you had this in the beginning, okay, your x squared plus y squared plus z squared equals to c squared d squared, and then you apply Galilean transformation. So we do it in with a negative sign here, for example. So I have that, okay, so that in your dash frame, this becomes that, okay, and also this also equals to that, okay. And what happens in this particular case, okay, in the O frame it looks the same, okay, it's a light cone in this way, but in the O dash frame, I think you need to think a little bit how this actually works, okay. In the O dash frame, it's going to get tilted towards the x-axis, okay. Okay, it's towards the x dash axis because of this addition of this component. So in other words, in the case of Galilean relativity, then your light cone gets tilted under the light cone under uniform motion. Now, this is going to be strange because what given a particular frame which is moving, then your light is actually propagating with a different speed in some direction. Okay, whereas in the usual case, you always think of light propagating with the same speed in all directions. Okay, so in this particular case, it's not. So that tells us something with respect to the physical laws involving light. There seems to be a preferred inertial frame, okay, so that your light cone is actually like this, meaning it's a perfectly symmetric case. So in other words, all your propagation of light in all directions are just the same speed, okay, and for that frame it's the preferred one because that is the one we actually observe. But there are other frames that seems not to obey this. So that is the implication of applying Galilean relativity to light. So that causes a problem in some sense. I think that's the end of this particular lecture. So let me move to the other one. I think we have about 10 more minutes, so let me just get into this lecture. So we have seen that your light cone gets tilted when you have uniform motion inertial frames. So this essentially is not, well, I mean, it's allowed in Galilean relativity. So in other words, what happens when you define Galilean relativity, you actually define it with respect to the laws of mechanics. You are not defining your inertial frames with respect to the laws of other physical laws like, say, electrodynamics. Okay? So that causes a problem when you try to unify some laws which is supposed to known to work for magnets, but when you have a different law, for example, for electrodynamics for light, for example, and try to implement with the same law as the mechanical case, then you find some problems. Okay, so let's understand a little bit about waves. Okay, so electromagnetic waves, which is light is your visible light is part of electromagnetic waves, are essentially oscillations of your electric and magnetic fields. Okay, so that's why it's called electromagnetic waves. Okay, and it's known that it's supposed to propagate with a constant speed. Okay, and this speed, which is also another important thing, is actually finite. It's not infinity. Okay, and this is crucial because it also helps explain some physical phenomena. Okay, so the idea of finiteness of speed of light was perhaps in the modern sense came to the Italian physicists first, but the idea of the finiteness of speed of light was actually observed, well, was actually deduced by Biruni in earlier century. Okay, so this is the text, the translated text, of course, okay, of Biruni having a dialogue with Ibn Sina. Okay, but why is it important to physics? This is probably in the modern sense because one could explain some physical phenomena. One of the things that people observe is, for example, the satellite of Jupiter. I don't know how to pronounce this thing. Is Io. Okay, it's a satellite. It's one of the moon of the Jupiter. And what happens is when they try to observe the eclipse of Jupiter, this satellite of Jupiter, at different parts of the Earth, okay, they find some discrepancies. Okay, so essentially this was explained by Romer, okay, by saying that, okay, well, actually Cassini mentioned this in the beginning, that is this discrepancies is due to the finite speed of light. Okay, but the explanation is more quantitative by Romer. So he was able to draw some geometric diagrams over here. So here's the orbit of the Earth, okay, around the Sun. Then here is essentially your satellite of Jupiter here, and then trying to figure out how the light rays coming from the satellite of Jupiter to the various points of the orbiting Earth here, and then you can actually explain some of the discrepancies. Okay, so I'm not going to go into detail. You can read some explanation of this inside one of the reference book I gave you. Okay, so essentially that can be explained quantitatively. This idea of discrepancies between the different observation of the satellite eclipse. Okay, but what's important is coming from the fact that your light is not instantaneous. It doesn't have an infinite speed, but it's actually a finite speed. That's the most important thing. Okay. Secondly, they started to actually calculate the speed of light. Okay, the first guy who did it is Huygens, and he gives you around this value, and then Newton himself actually calculated it to give this value, which is, I mean, it's a bit below the speed of light that we know. Okay, so it's despite that no, this is not really mentioned in most books. That but the idea of finiteness of speed of light is actually important to describe phenomena, and this become more prominent. Okay, when you do special relativity. Okay, so I think I should stop now because it will be going to a different topic here. So I should now take your attendance. So we have 20 people here. Okay. So, okay. So any question before we leave?
The chat.
Okay. Sorry. In the Galilean transformation, there is y is negative vt. Well, actually, I'm okay. If maybe I'll go back to this picture. Let me do it. O will observe. Suppose this is O, and then I'm trying to describe O dash, and O dash has velocity v. Okay, remember that the thing that I wanted to do was to describe let's suppose I have some event here. Okay, the thing that I wanted to do is essentially y v y dash z dash. The thing is I wanted to use these coordinates. Okay, if you look earlier, what was the thing that I wanted to describe? That's from lecture 2. I wanted to see what happens to the coordinates of your light cone. Okay, so in order to see the coordinates of the light cone, the spatial coordinates with respect to O dash must be compared to the spatial coordinates with respect to O. Okay, remember that in this particular case, I should be getting x equals to x dash plus vt. Okay, so to invert this, I should have x dash equals to x minus vt. That's all that is. Is that okay? Is it to say that motion of the new frame is going? I'm not quite sure what you meant by that, but essentially the idea is this picture. Okay, this is how O sees O dash, but now what I want is to see how O dash sees O, roughly speaking. See, and then you'll be able to see that okay, with respect to O dash, I see O moving on the opposite direction. Is that okay? Can or you can verbally say it out. Okay, good. Any other questions before we finish? I think it's already 9. I guess not. So we'll continue tomorrow. Okay. Hopefully, if there are more questions, you can ask tomorrow. Okay. So I'll stop there for today. Okay. Thank you, everyone. Bye.
Thank you.
Okay.
Thank you.